All right, I'm going to start the second part of this video talking about probably the two most difficult things, which are related rates and optimization. And I'm actually going to go away from the review. I know I've got some questions on here, one question of each on the review. Now, the related rates problem that I have on here is just Pythagorean theorem. Should be pretty easy. But I'm going to go actually to the related rates problems that I have on the worksheet that you did over related rates and optimization. Just the idea of doing a related rates problem, right? So anytime that you have, like most of the time they're geometric shapes, right? And we have changing quantities. Basically, what we want to do is we want to find the formula. We want to take the derivative of the formula, and that's going to introduce the rates over time. And then we're going to look at the question. We're going to make sure that we have those rates in our question. So this one is dealing with water creating a circle on the ground, and the radius of the pool is increasing at a specific rate, and we want to know how fast the area is increasing. So we need to come up with a formula for a circle that relates radius and area. So that's the area of the circle. Area equals pi r squared. We take the derivative of that, and remember with respect to time, so we do dA over dt. It's the derivative of area. We still do our derivative rules. So I multiply the two down, and then I chain on the derivative of that variable. So the derivative of r is dr dt. We have the rate that the radius is increasing. We're being asked how fast the area of the pool is increasing. So we're looking for dA dt, that's our other rate, when the radius is 5. So it's giving us r at that time, which means if I just plug in both r and dr dt, then I've got my answer for dA dt. So that's a very basic related rates problem. If I go back to the review, this one's Pythagorean theorem. We've got a plane that's flying horizontally straight across the sky there at 500 miles per hour at a consistent altitude of 3 miles. It flies over us, and we want to track the distance between the plane and us. So we've basically got this right triangle here. And we're concerned about the side lengths of that. So that's Pythagorean theorem. Take the derivative of each one of those. And then at that point in time on this problem, you've got 6 variables, right? So we've got x and dx dt, and then the same for the other 2 variables, y and dy dt, and so forth. The x, y, and z, those are at the moment we're concerned about, right? So we do know that y is always going to be 3 because the plane is flying at that consistent altitude of 3. So that's why y is 3. And that's also why dy dt is 0, because y is not changing, right? It's always 3. How fast is the plane's distance from you increasing the moment when the plane is flying over a point on the ground that's 4 miles from you? So the plane is then, it went over top of us, but now it's 4 miles to the, say, east of us, right? So x would be 4 at that time, and dx dt would be how that side length is changing. Well, that side length is changing at the speed of the plane, which is 500 miles per hour. The question is the distance between us and the plane. That's z. I want to know how z is changing. So what I'm looking for is dz dt, and I have to do a little bit of algebra here, or geometry, to get z at the time that this is 4. Again, this is always 3. At that specific time, this would be 5 if I use the Pythagorean theorem. That's why I have 5 here. And then I just use some algebra to solve for dz dt to get that 400 miles per hour. So a couple of pretty basic related rates problems. I would not concern yourself with like the really difficult ones that we did. I would stay in that lane. Okay. Same thing with optimization. So the optimization problem that I have on the review, it's number 5 in this section. It's pretty difficult. But the main idea of optimization is that you are either trying to maximize or minimize some quantity. So in this problem from our worksheet that we had over this, we wanted to find the dimensions of a rectangle that has an area of 1,000 whose perimeter is as small as possible. So we draw the picture. We want to minimize the perimeter. We want perimeter as small as possible. So we're trying to minimize the perimeter of that. The perimeter would be 2x plus 2y. Your goal is I want to create that equation where I only have one variable over here. I don't want both x and y. So that's where we use our constraint. The constraint is that the area has to be 1,000, so x times y would have to be 1,000. It doesn't matter which one you solve for, but I solved for y by dividing by x, and then I plugged this in for y up here in this equation, which is what you see here. Now I just have a function of x. I brought the x up, made it a -1 exponent, and then to find a minimum or a maximum, you use the first derivative. So I took the derivative of that, which is just derivative of that is 2. The derivative of this, I would multiply this down, subtract 1. I get this, and then I set that equal to 0, and I solve. This thing that you factored out, remember, you don't really ever have to set that equal to 0. I'm really just concerned about setting this part equal to 0, which gives me the square root of 1,000, or 10 root 10. I would want to make a number line to verify that that is a minimum, which it is, and then I would then find y by going back to my constraint equation. I would use the one where I've actually got y by itself here, and I would plug in that 10 root 10 for x to solve for y, which would also be 10 root 10. So we actually get a square in that case. But the idea of an optimization problem is you got two equations always. You got a constraint. You got a function that you're either trying to maximize or minimize. You're going to do substitution, take the derivative, set to 0. Okay. Again, I would focus on probably the easier-ish examples that you have of optimization to be prepared for that. So I'm going to go back to the review. I'm going to jump down to integration. This whole unit of integration, what I would focus on is being able to just solve an integral. Okay, so if it's an indefinite integral, which means it doesn't have bounds, you're just doing antiderivatives. Do not forget to put plus c. Okay, but just do the antiderivative of each term, put plus c, and you're done. If it is a definite integral, I'm going to skip down the ones that I didn't use u substitution. I'm not saying u substitution won't be on there, but I just want to focus on the idea of solving a definite integral, and then we can talk more about u substitution in class if we need to. But if it's a definite integral, which means you have bounds, the goal here is, again, just take the antiderivative of this, which gives me these three terms. And then remember what you do is you plug the top bound in first, minus, plug the bottom bound in second, and then you just work through the algebra there to get your answer. Okay. So can you just solve an integral, whether that be an indefinite integral where you're just taking the antiderivative and that's it, or a definite integral where you take the antiderivative and then plug in the bounds and subtract? Hopefully you can do that. That's what I'm looking at for integration. Again, u substitution might come up. We can talk about that in class. I did want to jump up here. I have a question on the final, and I put it on the board, that deals with position and velocity and acceleration. You need to know that it's position to velocity to acceleration. So if position is f, velocity is the derivative of that f prime, and acceleration is the derivative of that, which is f double prime. If you know that relationship, no matter what function I give you, you should know which way you need to go to get what you need. So on this question on the review, I give you the velocity. Here's the velocity, right? So I'm giving you the middle function. Question A asks about the position. So what do I need to do? I need to go backwards. I take the antiderivative of that. It does tell me the initial velocity s of 0 is 0, which tells me that c is 0. But then I want to know the position at time 2, so then I would plug in 2 to my position function. Again, c is 0, so I don't need to worry about that, but I get that. Okay, but that was an antiderivative. Part B asks about the acceleration. So if I had velocity to find acceleration, I got to take the derivative. So I did the derivative of velocity to get my acceleration function, and then I want the acceleration at time 3, so I plugged in 3. Okay, it's a great question. Dealing with position, velocity, acceleration, because I'm giving you the middle one, so it's requiring you to do both an antiderivative and a derivative in the same problem. All right, I'm going to jump down. I believe the last thing that I need to cover is in applications of integration. It's the volume stuff. So I'm going to jump down until I get to the volume stuff. So when we do the volume, this should be pretty fresh, hopefully, in your mind. You make the graph of these, right? So we graph the cube root of x and 1/4 x. So in this case, this function right here on top is the cube root of x, and the function that is on the bottom is 1/4 x. Okay. What you have to do, we're going to rotate this around the y-axis. Okay, so I mirrored that region about the y-axis, put it over here, and so forth. Remember, what you need to do is determine which way the rectangles need to go. So if the rectangles can stand up, which they can, because if they stand up, notice red would always be on the top, black would always be on the bottom. We're good. If the rectangles stand up, then what shape is created? Well, this would be a shell, a cylinder, right? If they stand up, you're stacking them from x to x, right? So we're stacking them from 0 to 8 is where that would be. That's where they're stacked. So that's where I get these bounds on my shell. Formula for a shell, 2 pi RH. So we got 2 pi, so we just need r and h. Remember, the r is typically just either x or y. In this case, it's x because it's an x distance to that where that rectangle is at. That's our radius. And then the height of that cylinder is just the red function minus the black function, which is what we have here. So this is the radius, this is the height, and then we've got our dx, that is the thickness of the shell. And then remember, you can plug that into Desmos to get that answer. Okay. Now, why do I have the other one on here? Well, this is a problem that you could have done either way. So I'm going to erase this and start over with the other shape. The other shape, the washer would be created if my rectangles were laying down. So if my rectangles were laying down, that works as well, because if I lay them down, again, the red function would always be defining the left, and the black function down here would always be determining the right, so I can lay them down. Well, if I lay the rectangles down, then that means they're being stacked vertically, which means they're being stacked from a y value of 0 to a y value of 2, which is where we get these from. Those are y values. Okay, so we've got this washer. It looks like a disc, right? A CD, something like that. Okay, so volume of a washer, that's pi r squared minus pi r squared, right? We take out the pi, so we just need the outside radius and the inside radius. Well, if your rectangles are laying down, then that means these functions need to be not in terms of x, but in terms of y. So I went up here and I changed these. I solved both of those for x so that I have those functions in terms of y. And then it's simply just my outside radius would be the black outside function. So that's 4y. That squared minus the inside function squared, which would be y cubed squared dy. That would give me the same exact answer. Okay, so I gave you a problem here on the review that you could do either way. Remember, that's not always the case. But remember, the key for figuring out which one you have is, what I think the key is whatever our axis of rotation, in this case it was the y-axis, compare that to a rectangle, right? If the things are parallel, if the axis of rotation and the rectangles are parallel, then you get shell, which is why these standing up rectangles around a line that stands up gave us a shell. If they are perpendicular, so I've got my line, my rectangle here, right, versus my axis of rotation here, those are perpendicular, then I'm going to get a washer whenever I rotate that around. Okay, so I think that's the key, is being able to figure out which way the rectangle need to go. What shape do I get from that? That's the important part here. And then being able to write those out. Okay. I will say, just for those of you taking the time to watch this video, that I will be giving you the formulas for shells and washers. So it'll look something like hey, a shell is 2 pi a to b of, say, f of x dx. So you just remember that this is the radius, this is the height. But I'll be giving you these formulas, so you don't necessarily have to memorize that. That'll be part of your formula sheet. Okay. I gave you a second one here on the review, but it's a little bit more involved because you're rotating around a line that's not the y or the x-axis. Adds an element of difficulty to it. I wouldn't worry too much about that, but that is what you're going to see when it comes to the test on volumes. The last page of the review is differential equations. It's not written on the board, okay? So feel free to work through that, but I'm going to need that for the final. So with the first video combined with this one, I think I've gone through basically everything you need to know for the final. Take some time to work through that. Again, my goal is not to give you the most difficult kinds of questions that I can. It's to make sure that you know how to do each kind of problem that is the most important to walk out of calculus knowing. So happy studying. Good luck on the final. If you have questions, again, bring those to class. We can talk about those then.